Welcome back everyone. In the last lecture, we had seen how can we convert signals into mathematical objects. Basically, signals are nothing but functions, and I also told you about the meaning of systems as mathematical objects. Those are basically operators. In today's lecture, we will see what are the different types of systems that we would be dealing with in this course. So, basically there is this single input, single output system. So, depending on the number of inputs and outputs of a system, we can differentiate systems as SISO systems, single input, single output systems. Now, what is a single input, single output system? You will have single input and single output. A typical example, I will show you a typical example. A typical example would be something like this. So, this is a DC motor, okay, and to the DC motor you have an input, the input terminals here. The input given to the DC motor is a DC voltage. So, if you look back, you see we have 3.1 volt given to the motor. So, based on that, you see what the motor is doing, the motor is rotating, okay. Again, if I change the input to say some other value, 4.7 volt, see the speed has increased. So, what is happening here is that the input to, there is only one input to the system, which is a voltage input. So, in this example what we have shown just now, so it is a DC motor, the input to the system is a voltage input, and what is the output of the system. Now, this is very essential, okay, to identify what the output signal is, and this will be very essential in this course because we are trying to get to the desired output, right, as a control engineer. So, we should identify the output correctly. If we do not identify the output correctly, then what is the we will not be even able to solve the problem. What is the output in this case? Now, you have the DC motor, okay. Now, there can be many things that you can do with the DC motor. So, the first may be speed, okay. Why speed? So, if I go back to the drone example. So, in this drone, suppose this drone has to go up and down, okay. So, which means that the speed of these motors must increase to go up, okay, because when the speed of the motors will increase, it will give thrust, more thrust, and this drone will go up. How and why, I mean all that will come to later, but in general basic physics will actually help you understand that. You see, if I increase the speed of this motors, that means if I increase the speed of the rotors, then it will go up, or decrease the speed, it will come down, right. Now, so think about it. In this case, if I just concentrate on one of the motors, okay, what is the output in this case? The output would be the speed of the motor, okay. Suppose this was not a quad rotor but a single rotor device, okay. Basically, there was only one rotor, and based on that one rotor you are going up and down, okay. So, that means there is only one rotor, okay. So, now suppose you want to go up, you will increase the speed of the motor. If you want to go down, you will decrease the speed of the motor. So, in this case, what you are trying to control, or what is your desired signal, desired output signal, it becomes speed, because with the help of the speed only you can change the position of the device or the system. So, in this case, in this example that I have just now told, your output of the DC motor becomes speed, okay. So, Vt theta t or theta dot t, theta dot t means the angular velocity of the motor, the motor shaft, okay. Now, if I take some other example, let us think of it. Suppose you have a motor, okay. On top of that, suppose there is an antenna. You at your home, you have those TV antennas, right? I don't know nowadays people use it or not, but we used to have it. I mean, these antennas, big antennas were there, dish TV antennas, or those other antennas that we used to have. So, if you have an antenna, okay, you can always think of it like, suppose you want to automate it and you want to rotate the antenna. Okay. Now, suppose you want to rotate the antenna, you will connect a motor to the base of the antenna, okay, and suppose you want to rotate the antenna to say 30 degree. So, the position of the shaft of the motor should rotate the antenna to 30 degree, 60 degree or some other degree. Now, in this example you see the desired or the output is the position of the shaft, not the speed, because if I say that I want if my desired output is that the antenna should move to 30 degree, then my motor shaft should rotate to 30 degree position. So, which means that the output signal in this case we will consider as a angular position. So, in that case your output becomes theta t. So, from this at least you should understand that to identify what is the output signal and of course the input signal is very important, because if you identify that correctly, then you have actually gone to the next step. Okay, now that you know what the output signal is, what the input signal is, now we can ask the question, if I want my output signal to be something, then what should be my input signal. Okay. So, now that you are starting this course, you should always understand that identifying the signal is very important. Which signal are you trying to control? Which signal is the input? Which signal is the output? These are very important questions. Okay, fine. So, now let us go to the next type of system, which is a multi-input, multi-output system. Of course, if the first one was single input, single output, you understand the next one has to be multi-input, multi-output, and we call it MIMO system. Single input, single output is seesaw system. Now, what can be an example of a MIMO system? Okay, the drone that I showed you. Okay, so I will show you another video. So, here we have this drone. Okay, so this drone is being controlled by this joystick. Okay, so if you change the position of the joystick, the drone will also change its position. You see, and you can directly see that there are multiple inputs here, because there are two joysticks to start off with, and actually there are 4 inputs, which is basically you can move your thumb to the front, to the right, to the left, and the drone will also move accordingly. So, directly you can see that this is a multi-input system. Okay, the input to this system there are multiple inputs to this system. To directly visually you can see that there are 2 joysticks. So, of course, there will be minimum 2 inputs, but actually there are more than 2 inputs. There are 4 inputs in this system. Again, how are there 4 inputs? What are the 4 inputs? I am not going into that now, but we will go into that later in this course. Okay, fine. So, what are the other types of systems? The other type of system is a linear system. Okay, a system is called linear if it satisfies the principle of superposition. So, I hope all of you know what superposition is. If you do not know, fine, I'll just revise it again. Okay, what is superposition? Superposition consists of two main ideas. One is additivity and one is homogeneity. Okay, so a system is called linear if it satisfies additivity property as well as homogeneity property. And what is that? So, if U1 is the input to the system and Y1 is the output of the system, okay, and if U2 is a input to the system and Y2 is an output of the system, then if you give U1 plus U2 as input to the system, the output of the system must be Y1 plus Y2. This is additivity, and remember, this has to be true for any kind of inputs that you take. You cannot just say that, oh, for 2 inputs it works, that means that it will be linear. No. Okay, I'll show you what I mean by that soon. Homogeneity, if you give U1 as input to the system and Y1 is the output, then for alpha of U1 as input to the system, the output would be Y1, alpha of Y12, where alpha here is a scalar quantity. Okay, so the definition looks very simple. So, that is what a linear system is. Okay, what is a non-linear system? Of course, a system that does not satisfy any of them or one of them also. If it violates, then it is a non-linear system. So, it should, if it does not satisfy the principle of superposition, then it is a non-linear system. Now, I will show you a video. Okay. So, here is a system, it's a black box, I am not showing what is inside it. Okay, here we have the input to the system and we have the output of the system as well. Okay, so let us see how does the system behave. So here initially I am giving 1 volt as input, and look at the output of the system. The output of the system is, so let the cursor go, so it comes out to be I think 1.7 volts. Yes, 1.7 volt is the output of the system for 1 volt. Okay, let us look at 2 volt. So when we give 2 volt, the output of the system is 3.7 volt. Okay, so you see for 1 volt it is 1.7 and for 2 volt it is 3.7. So if I give 1 plus 2 3 volt, which is basically U1 plus U2, if I give 3 volt, I expect, if it is a linear system, I expect that it should give out 3.7 plus 1.7, 5.4 volt. Let us see what happens. You see, it is 5.7 volt, not 5.4 volt. So you can directly say that this is a nonlinear system. Okay, the system that was inside that box is a nonlinear system. Okay, actually it is a simple RC circuit with a diode at the end. Okay, that was the circuit actually, I mean simple circuit. Now you see, think about it. If I again, let me just go back to the video again. I have to show you something. So, okay, I am going back to the video. See, now I give 0 volt. Okay, so the output is 0. Output is 0. Okay, now think about it. Okay, suppose you had done this experiment at the beginning. Okay, we took our U1t as say 1 volt. Okay, output that we got was Y1t was I think 1.7 volt, right. Suppose you took the second input as 0 volt and the output was 0 volt. Now notice, then what is U1t plus U2t? This would have again come out to be 1.7 volt only, right, because U2 is 0. So does it mean that the system is linear? Because it is satisfying, you see, this is equal to Y1t plus Y2t. So it is satisfying the linearity property, looks like that. Okay, but that is not true, because when a system is linear you have to check it for every possible pair. Okay, so for example, when we took U3, when we took U3 to be equal to, if I am not wrong, 2 volt, our Y3t came out to be 3.7 volt. Okay, but when we took U1 and U3 together, we got 5.4 volt, which is not equal to Y1t plus Y3t. So if you come up with at least one pair for which this either additivity or homogeneity is violated, you can say that the system is non-linear. But to say that a system is linear, you actually have to show that for all cases this is true. For all cases additivity and homogeneity is satisfied. You cannot check for only one pair and say that, oh, the system is linear. No, you have to check for all cases. Now of course you understand, is it possible to check for all inputs? It is not possible to check for all inputs, and that is where maths will help us, because now what we have done is, using maths we have taken the system and then made it into a operator. Okay, and then we have taken the inputs and made it into functions, and then using that we can try to see if the system is linear or non-linear. Okay. I'll take an example in the next class maybe, but let me go ahead and finish what are the types of the systems in today's class. Okay. So, the other case is a time invariant system. A system whose behavior does not change with time is called a time invariant system. So, mathematically how do we represent that? So, if the output of the system is y1 when you give u1 as input, then the output of the system should be y1 t minus tau if you give u1 t minus tau as input to the system. Basically, if you give a shifted signal as input to the system. What is the meaning of that? The meaning of that is, suppose you take a system today, you gave input to the system, you got an output. You come back tomorrow, okay, and give the same input, the same output should be there. You should get the same output. So, what do you mean by tomorrow here? It's a time shifted input, right? You are giving the same input tomorrow. That means it's a 24-hour delayed input, say. Okay, but still the output also is 24-hour delayed. So, what do you mean by 24-hour delayed? Because you are starting your timing from today, and tomorrow after 24 hours you are checking again the output of the system based on the input that you have given today. Okay, is it practically our systems time invariant? Depends. Okay, most of the cases it will not be time invariant. Okay, but time invariance practically has you have to understand it from a different point of view. So, for example, suppose let's take the example of a drone itself. Okay, you are flying the drone today, everything is fine. Okay, suppose you have a motor, you give input to the system, to the motor, it will rotate, motor as in the rotors of the drone. Okay, it will rotate at the, you give to some input voltage, it will rotate at particular speed. Tomorrow also it will rotate at particular speed. You keep on doing this for say 2 years, after some time there will be change in the speed. Why? Because there will be wear and tear of the motor, because of that there will be change in the speed. The same input will not give you the same output. So, that makes the system time variant, right? Because with time the output of the system is changing for the same input. Okay, so it becomes time variant. But does that mean we should not study time invariant systems? No, because in a shorter run it is a time invariant system. So, because if you look at suppose 1 week, 2 week or a year's time, the drone will work as it is for the same input, same output you are getting. Okay, because the wear and tear is negligible in that case. So, for that amount of time it is time invariant. So, whatever we study for time invariant systems we can apply for a drone in that case. This is just a simple example. So, the idea of invariancy actually depends on up to how much time you can tolerate invariance in the system. So, for example, in case of the example that I just now gave, for 2 years, 3 years, suppose you do not want the drone to work for 2-3 years, suppose you just want it to work for 1 year and then you will replace it. So, it is fine, you can use this the results of time invariant systems then. Okay. So, similarly, what is a time variant system? A system whose behavior changes over time. Next, we have a causal system. What is a causal system? A system where the output at any given time depends on present and past values of the input and does not depend on the future. If you have a system, whatever input you are giving to the system, the output of the system should depend only on the present value or the past value or both. It cannot depend on the future. Okay? Then we say that the system is causal. Non-causal system, of course, if the output of the system depends on future, then we say that the system, then it's a non-causal system. Then a question to ask is, what is a practical example of a non-causal system? Because causal system looks very like practical, right? How can I know the future input when we are giving an input to a system? How can I know the future input? Right? Think about it. I cannot know the future input. So, that means that why do I even have to make this distinction between causality and non-causality if in practical scenario we do not even get non-causal system? But that is not true actually. We get non-causal systems, and the example for that lies in audio processing, image processing, etc. Okay, I'll show you an example. So, here is the code. So, what this code is doing, let me just explain that. So, it is taking a CSV file which is a signal data. Okay, suppose you recorded something, okay, recorded an audio file. Okay, it's a signal, audio is a signal, right? So, audio signal you can take the samples of that signal okay, and stored it in some CSV file. You have stored it in some CSV file, which is this, okay. So what I am doing is I am taking that file, and then what I am doing, I am not going into the details of the code. I will just try to explain you what I am trying to do here. So what is being done is, so I am taking different samples of the audio signal. So at n equal to 0, suppose it had some the function had some value, say 0.5 example, okay. So at 1 it has suppose 0.6, at 2 it had 0.7, 3 0.8, so on. So this is also a signal, right? And say for some reason there was noise in this signal for whatever reason, okay. This is a noisy data, say, and I want to filter the noise out, okay. Now if you look at it as a signal perspective, what I can do is I can take the output of the signal in this way, 1 by 3 times xn plus 1 plus xn plus xn minus 1. What I am doing basically is, at suppose y0, what is the value of the output at y0? So what I am doing, I am taking this function or this signal, and then I am post processing it, okay. How am I post processing it? Y of 0, the new signal that I get is equal to y1 x0 and x minus 1. So x minus 1 is not there, so I am not taking that. These two I am averaging out basically. So y1 will be nothing but 1 by 3 x of 2, x of 1, x of 0. So it is an average of 3 signal points. But notice one thing, the output, the index of the output is n equal to 1, and notice at the inputs that you are choosing to get the output at n equal to 1, you are taking n equal to 2, n equal to 1 and n equal to 0. So it is so at n equal to 1 you are taking a value of the input which is future, right, corresponding to this example at least. So this is a non-causal system. So in this type of examples or in this type of scenarios, you actually end up in non-causal systems also. So of course when you talk about time domain signals like the ones in quadrotors or in these type of cases, you might not get a non-causal system, but in general you can have non-causal systems. Here is an example. So let me just go back to the code that was there. Let me just run it. Basically the code actually is this only, whatever I have just now explained. So this is the original signal. You can see that the signal is quite noisy in that sense, okay. So this is a original signal, and I did the same filtering that I have just now explained you. I am taking the average of 3 samples, and you see, you can look at it and you can see that there is nice smoothing of the signal, okay. So in signal processing, non-causal systems are very important, especially in image processing and all. We can actually, whenever you can actually store the signal, you can go ahead and use a non-causal filter, okay. And so that's how a non-causal system arises. Now till now we have talked about these different types of systems, okay. Now for this course, what we are going to do is, we are going to limit ourselves to linear systems, time invariant systems and causal systems only. So we will only talk about linear, time invariant, causal systems, okay. You might think that, does it limit us? Yes, it will limit us, okay. But if you understand these type of systems, you will see that we will be able to use it in non-linear cases also. Now, especially if you understand linear system theory related to linear systems, linear time invariant systems, you will be able to use the same for non-linear systems. Of course, with some caveats, we will have to do some assumptions and all. In this course, at the end, we are anyways going to talk about quadrotors, which is a non-linear system. So although we are restricting ourselves to LTI system, you will see that whatever we study in this course can be translated, can be used to study a non-linear system as well, of course with some caveats, okay. But we have to start from a linear system because we cannot directly understand a non-linear system otherwise, okay. So till now we have seen what are the different types of systems we will be dealing with in this course. In the next lecture, we will see how do we find the operator that I was talking about in these lectures. Thank you.